All right. So welcome everyone. This is week 17, our 17th session, and today we will discuss new topic: reinforced cement concrete. Okay. Uh, so today we will discuss our quota questions both on the development concept, and then we'll have a look at two simple questions just to revise the concept of WSM and LSM. Right? Even though WSM has not been asked many times and it is even become obsolete, still we look at some concept which may be which can be asked in the WSM or in GATE and DSC. Alright, so let's start. GATE 2015 question number 18. The development length of a deformed reinforced bar can be expressed as 1 by k phi sigma s divided by tau bt. From IS 456-2000, the value of k can be calculated as. Alright, so to solve this question, we need to know why do we provide this development limit and how does it function. So consider this as your concrete section, and you have and then you have a beam. This is your support. Let's say this is your support, and somewhere here another there is a support, and then in the between you have provided some beam, right? And then there are a lot of reinforcement bars that are going from that are being provided inside this particular beam to support the loads that we are giving. Now if we want the structure to be safe, because what can happen is the beam may be able to take the load, but if it is not properly bonded with the supports, it may fall, right? It may fall. So to avoid that, what is done is these reinforcements that we can see here, these reinforcements, they are extended, into the support by some length. They can be either straight extended, or they can be at some angle, but we are looking at straight only. So they are extended into the support to provide additional uh, strength to the joint, apart from the concrete being providing the strength. All right, so that is the reason why these development lengths are provided. Now, how do we calculate this length? So let's say you have loaded this particular beam, some UDL or some point load. In that process, the beam has developed some kind of stress that we call as sigma st. Right? Now this sigma st will be tensile, because that's why we are using reinforced bars to provide tensile strength to our concrete beams, right? To our RCC beams. So this will be tensile. Okay, it is going to try to pull this particular joint out of that uh, out of the support, and the stress with which this particular steel is being pulled out will be same as sigma st, right? Because that is the stress that is developed in that. Okay, so what will be the force? Sigma st into pi r square, the area of this particular single reinforcement bar. Now, this concrete has a bonding strength with the particular steel. So here on the surface we'll have a bonding strength with the steel, and that is given as tau bt, and it varies with M20, M25, 35, and so on. M20 being the lowest bonding strength, and then M35 being the highest bonding strength. All right, and this acts on the surface of the particular uh, development length that we have provided. So if this is the development length, then what is the surface area? It is 2 pi r into LD. This is the surface area, and this is the kind of shear strength, or you can say the bonding strength, that is being provided between the concrete and the reinforcement. So this will be tau BD. So now what you do, this is the force that will pull this particular beam or keep this particular beam inside, and this is the force sigma st1 sigma st into pi r square that is going to pull it out. So if you equate them, then you should get nice enough formula for your development. So when you simplify this, you will end up with this formula. Alright, we can simply write this as sigma st pi by k tau bd. Alright, one thing to note here, that this is for mild steel under tension. Okay, and if it is HYSD sealed or deformed steel, the formula will be different, and if it is under compression, the formula will again be different. So what I am going to do now, I am going to erase these things here. I'm going to erase these things. I hope you have noted down, or you can go back to the video and then you can see what we have written. So let me write this here, and let me remove this also. Now let's make a column. So first is mild steel, second is high yield steel with which is deformed, and another condition is tension and compression. So if we make this 4 by 4, and what we are going to write here, we are going to write here the value of K. Where K is what? K is nothing but this particular variable. Okay. So what we saw, for mild steel under tension, K is equal to 4, right? Now, when you provide a high yielding deformed steel, in that case, tau BD increases by 60%. So tau BD will change, but its effect will be observed in the K. So 4 into 1.6, that is 6.4. Okay. Now when you are under compression, in any case, regardless of the case, when you are under compression, tau BD is going to increase by 25%. So in this case, it is going to be 4 into 1.25, that is going to be 5. And in case of HYSD, it is going to be 4 into 1.6 into 1.25, that is nothing but 8. Okay, so these are the values of K according to this particular question. Now what is asked of this question? We are asked development length of deformed reinforcement bar can be expressed as this. Yes, and we have been given deformed, and nothing is given to us with about compression or tension, so we are going to assume it is tension only. So the value of K in this case is going to be 6.4, and that is your tension. Alright, good. Now let's go to the next question. Okay, GATE 2013 question number 7. As per IS 456-2000, for M20 grade concrete and plain bar seam tension, the design bond stress tau BD is given as 1.2 megapascal. Further, IS 456-2000 permits the design bond stress value to increase by 60% for HSD bars. The stress in the HSD reinforcing steel bars in tension So this is bars in tension. If sigma is equal to 360 MPa, find the required development length LD for the HSD bars in terms of the bar diameter tau. So basically, LD will come out to be some alpha into phi, and they are asking us what is this alpha. Okay, so what do we know about our development length? We know that it is the surface resistance from the concrete and steel bonding that is resisting the pulling out force because of the stress developed in the steel. So it is 2 into pi into r into LD. This is the surface area that is being used by the bonding between the steel and the concrete into the bonding strength is equal to sigma s, the stress in the steel reinforcement bar. Hello, and that will be multiplied with the area of the steel, which is nothing but pi into square by 4. Okay, so when you write this clearly, it is going to be, after simplification, it is going to be like this. Now, what is told to us? What they have told to us? They have told that sigma s is 360, diameter is unknown, and this is a HYSD bar, right? This is a deformed bar. So we have to increase this 1.2 by 60%. So 1.6 into 1.2. So this is going to be our answer. So this is alpha into phi, and alpha is 360 divided by 4 into 1.6 into 1.2. That is nothing but 46.875. And this is the answer to this question. You should remember that whenever we have HYSD bar or HSD bar in this case, then tau BD increases by 160%, and when the steel is in compression instead of tension, then tau BD increases by 1.25%. Also, if it is HYSD bar or HSD bar, deformed bar, under compression, then both will be applied. Right, so it will be 1.6 into 1.25 if both are there. Just remember this. All right. All right. So those were our quota questions that we were required to finish. Now we are going to look at some more interesting questions, and I hope that they can help us in enhancing or making us more familiar with our concepts. Okay, let's start. First question. For a beam of size 500 mm into 700 mm effective depth, calculate the area of steel required for the beam for a bending moment of 300 kN using M30 concrete and Fe415 steel by WSM method. Okay, so we have a beam, some reinforcement is there. This is a 500 mm and this is a 700 mm effective depth. So B is 500, D is 700. Alright. What else is given? M30. What does this mean? This means FCK is 30 and sigma CBC is nothing but FCK by 3, that is 10 Newton per mm square. Now, we have FE FP 415, that means Fy is 415, that means sigma St is 415 divided by 1.8 and approximately becoming 230 Newton per. Alright, so these are the allowable maximum stress that can develop in the concrete and in the steel respectively, according to WSM. Okay, so we have to calculate the area of steel required. So first, let us check that whether the balance moment or the limiting moment, let us call it as limiting momentum, MU limiting, what is the value of that? Whether it is greater than this 300, then we can easily provide an under reinforced beam and get away with it. If it is less than 300, then we have to go for double reinforced beam. But in case of if they are not specifically asking about what is the area of the reinforcement that has to be provided on the compression side, then you don't go for double reinforcement, then you have to go for single reinforcement only. So let us see. Alright, so for this thing, what do we want? We want XU limiting, right? Now let us revise some concepts to know how do we calculate XU limiting. So in WSM method, if you remember, I think you all know in LSM method that the design or the stress diagram looks something like this, right? So this is 0.87 Fi, 0.67 FCK, then this thing, this thing is 3 by 7 XU. This is 4 by 7 XU. So this is the neutral axis. I'm just writing it for your reference. So you know this diagram, right? In the LSM method. But in case of WSM method, we assume a homogeneous mixture of concrete, which is linearly elastic. So the stress diagram also comes out to be like this. Although we ignore the strength of concrete below this particular below the particular neutral axis, but still this is linear. So if this is FCBC, this is going to be FST divided by M. This is a stress in concrete. How do we get this? We get this from the compatibility equation. What is compatibility equation? This equation states that the strain in concrete will be equal to strain in steel at the point where they both are present, at the point of reinforcement. So the strain is nothing but stress divided by your modulus of elasticity. So it is nothing but Fc divided by Ec. This is nothing but Fst divided by Es, and Fc is equal to Fst divided by Es by Ec, and we all are familiar that Es by Ec is nothing but our modular ratio, right? So this is the reason for this. Alright, so I am going to make it smaller just so that you guys know that it was there, and we also have some area for the rest of the class. Alright, now you know this. Then this is going to be XU, this is going to be D, From similarity, FCBC divided by XU is going to be FST divided by M D minus XU. Right? This is your expression that you are going to use to calculate your XU limiting. So in case of in limiting scenario, what happens? FCBC becomes sigma CBC, FST becomes sigma ST. So you will have sigma CBC divided by XUL limiting sigma ST divided by M D minus XUL. Upon rearranging, what you will find that you can have a bunch of formulas for your neutral axis, limiting neutral axis. So you will have XU limiting equal to M sigma CBC. I'm writing the end result after the simplification that you can do on your own free time. Right? This is one formula. Another formula, you will get 280 divided by. So here I did a mistake. Instead of 3 sigma CBC, it should be 3 sigma ST, and I have corrected it in the coming slides. XU limiting. So, if you look carefully, you will see that this is quite similar to the formula which we have seen in LSM. Right? We are also going to look at one very similar question, in LSM also. So we'll look back at those formulas again. All right. So these are the formulas for your XU limiting. I'm going to highlight them, and I'm going to try to squeeze them in this first slide itself. Okay. So this formula will become smaller, and we're going to put this formula also. It is smaller. And if you are wondering why and how this 280 came here, so modular ratio, this M, which is the modular ratio given by ES by EC, it is given as 2 into 10 power 5 divided by 5000 root under FCK, which is called as short term. But for when nothing is given into your question, and particularly in design type of questions, you have to use the long term formula for your modular ratio, that is 280 divided by 3 sigma CBC. Right? This is the long term. It accounts for creep also. So for our question, we have M equal to 280 divided by 3 into 10. That is, calculate 9.33. Alright. So what is our LSM? Sorry, XU limiting. We have 280 divided by 280 plus 3 into sigma ST, that is 230, into D, that is 700. Alright, so here I have made a mistake. Let me clarify that. So here I put 3 sigma CBC, that should be 3 sigma ST. So make sure you have corrected this. Okay, so this is going to give us our XU limiting, that is 280 divided by 280 plus 3 into 230 into 700, 200 202.06 mm. Now, using this XU limiting, and since we don't know the area of steel, what we are going to do to calculate mu limiting, we are going to use the concrete side of our problem. We are going to use the concrete side of our problem to calculate mu limiting. So if you are familiar, how do we calculate this particular mu limiting? We calculate force into lever arm, right? So if you look at this particular force stress diagram, you see that the centroid is going to be from the maximum stress side 2 by 3 XU, correct? So this particular lever arm in this case is going to be this particular length, and that is d minus x du by 3, correct? And what is going to be the force? Force is going to be nothing but the area into the width, right? So 1 by 2 into FCK into XU into V. This is going to be the force, right? So let's calculate your moment of resistance using this particular formula. 1 by 2 to FCBC. Oh, my apologies. I wrote here FCK. FCBC BXU, in this case it is limiting, into D minus XU limiting by 3. When you put the values, you will see 1 by 2. So this FCBC is nothing but sigma CBC only, because we are trying to calculate the limiting scenario. 10 into 500 into 202.06 into 700 minus 202.06 divided by 3. So mu limiting is going to come out to be 319 point something kilonewton meter. Remember, whatever will come in Newton mm, and then you have to divide it by 10 power 6 to convert it into kilonewton meter. Okay, this is coming to be our mu limiting. That means we can actually design an under reinforced beam, right? Because our applied momentum after the correction factor and everything, after the safety factor, it is still less than our mu limiting. So we can go for under reinforced beam, right? And one important thing to note about under reinforced beam design in case of WSM is that you don't have to calculate your XU again. You don't have to calculate any other things again. You can just use this particular XU limiting, and you can calculate the area of steel. Just one change you have to do. Now you have, since it is under enforced or it is limiting, you have to say that sigma st is equal to fst, that is equal to, in this particular case, 230 Newton per mm square. Alright, yeah, so in case of steel, again you know that this lever arm is going to be d minus xu by 3, and the momentum is going to be fst into ast into d minus xu limit by 3. So we have 300 into 10 power 6, because we need to convert it to Newton mm. And fst is 230, because since it is under reinforced, let me make a remark here. Since it is under reinforced, FST will be sigma ST, right? And also your FCK will not be equal to your sigma CVC. Just remember this. Okay, so 230 into AST, change the color, into 700 minus XU limiting, that is 202.06 divided by 3. AST is equal to 306 divided by 230 divided by 700 minus 202.06 divided by 2061.73 mm square. This is your answer. C. One more note. Can proceed with x equal to x limiting. Right. So what I want to say to you now, that since it was under enforced beam, you could directly use your XU limiting. You didn't have to calculate anything else. Right? You could directly use your XU limiting to calculate your area of T. But if it was over reinforced, and how will we know whether it was over reinforced? When you calculated your MU limiting, using your concrete side, if in that case your MU limiting was less than 300, let's say it was 200, that means that concrete side, the strength in the concrete itself, it's not going to be sufficient to provide the appropriate strength to this particular beam. In that case, we will have to provide more reinforcement so that we can resist the given stress. In that case, we have to design an over reinforced beam. And when we have to design an over reinforced beam, we would have had to calculate your XU limiting again. Sorry, we cannot use XU limiting to calculate AST. We would have had to calculate our XU again, which will be the actual depth of neutral axis. And how we will do that? Let me quickly go back here. And how we will do that is, we will use this concept of similarity, FCBC and FST by M. So this is a stress diagram. We are going to use that, and we will say, since it is over reinforced, that means the concrete is going to reach the permissible stress. So we will have again the same expression of similarity, right? So in this same expression, we will put here sigma CBC. Okay. And using this XU, you will calculate the strength in your the stress developed in your steel. Now, how do we get this XU? You get this XU by equating your moment of resistance that you will get from the concrete side. So you will have something like this: 1 by 2 into sigma CBC into D into XU into D minus XU by 3. So using this 300 or something, let's say 400 if it was, you get this XU. And using the similarity, now you know the XU, and you know that the stress in the concrete is going to be sigma CBC. You will calculate this FST. Then you go back and then put that FST in this formula, and then the XU you calculated in this formula, and then you have to calculate the area of steel. Since it is under-enforced, it is pretty simple. Actually, in case of WSM, you can directly use, if it is under-enforced, you don't have to change your method. You can design it as same as your limiting uh, or balanced beam. Okay? Alright, I hope you got that. Let's move on to the LSM part of our problem. So let me erase this, because we are going to need the space. Okay, so why one of the reasons when I was making this problem that I understood why we have also made this WSM method obsolete is we see as we can see from this problem also that I have given the same amount of resisting moment, same dimension of the beam, same concrete, but I have reduced the steel grade. And even if I reduce the steel grade with a similar area of steel, you will see that I will be able to resist this particular momentum. Okay, so it means that LSM designs are more economical, you can say. Alright, so let's start. So the question is same. We have been given the same size of beam and same resisting moment, and we are asked what is the area of steel now according to the LSM. One change, I have reduced the grade of steel. So M30, this means FCK is 30 Newton per meter per m square, and FE 250, this means Fy is 250 Newton per m square. MOR, factored momentum, is 300 kilonewton meter. This is 300 into 10 power 6 Newton mm. Alright, now what we have to do? Same as we did in WSM, first we have to check whether our MU limiting is more than this 300 or less than 300 or greater than 300. So for that we will need XU limiting. Now what I want to show you guys is how we can get the formula for XU limiting in this case. Alright, so one more thing. So what we will do, we are going to do 3-4 things here. We are going to see the formula of how we are getting XU limiting, and we are going to calculate the compression forces in each of the sections. So you remember this stress diagram, we are going to calculate this, how to calculate this. Then I am going to tell you, I'm not going to do that, but I'm going to tell you how you can get this, as in the triangle there was only one block and we could get the centroid, because we all know that the centroid of the triangle is going to be from the 2/3 from the base, and 1/3 from the base, and 2/3 from the top. Yeah. So here I have made a mistake of writing 2/3 XU, the centroid from the base, but it should be 1/3 XU. Regardless, the lever arm I have written correctly here, so it is D by XU minus 3. So there is no change in the calculation. So as we know, from for triangle it is 1/3 from the base and 2/3 from the top, right? Of this height. But in this case, there are two separate boxes, one triangle, one rectangle, and then one kind of parabola. So we'll see that how this 0.42XU comes, or at least I will tell you guys how it comes. And then we are going to see our basic question. So we are going to clear some of our basic concepts. Now, in case of the LSM, we know that the strain diagram is the only diagram which is going to be straight. Stress diagram is not going to be straight. And what are some assumptions that we make in LSM? That the maximum strain in the compression in our particular concrete is going to be 0.0035, right? And maximum strain in case of our steel is going to be 0.002 plus 0.87 Fy divided by Ex, right? So this is the thing that I hope you remember. And then this is your depth of neutral axis, XU, and this is your effective depth, D. Now, same as we did in WSM, use similarity. 0.0035 divided by XU is going to be equal to 0.002 plus 0.87 Fy divided by ES divided by D minus XU. Upon simplification, you will see that we have the formulas for XU. In 2-3 forms, we can have the formulas for XU can be written as 0.0035 upon 0.0055 plus 0.87 Fy by ES. Or if you put the ES value as 2 into 10 power 5, you can write a much more nice looking formula. 700 divided by 1100 plus 0.875. Alright, so again I am going to make this shorter. This is the way how we have obtained it. So I am going to keep it here and I am going to just highlight this. So these are the formula for XU limiting. Alright, now let's calculate this XU limiting of ours. So 700 divided by 1100 plus 0.87 into 250. So what is the value of XU limiting? Then whole thing multiplied by 7. Our XU limiting is coming out to be 372 mm. Alright, now we have to calculate our MU limiting. But before that, let me tell you how we calculate the. So basically we want to calculate our MU limiting from the concrete side, so compressive force into the lever arm. So before that, let me tell you how we calculate our compressive stress. So let me make this a little bit smaller because I want to use this strain diagram to explain something. So let me take this diagram here. So this is your strain diagram. Let me extrapolate this neutral axis to some distance and draw also our stress diagram. So this is your stress diagram. Remember here that the one more factor of safety needs to be applied. So this will be 0.67 divided by 1.5, it will be 0.45. What we know that this particular stress profile in the concrete is rectangular to some distance and then it becomes a parabola. And to what distance we assume it to be rectangle? We assume that it is rectangle till it is parabola as far as the strain in this strain diagram is less than 0.002. So till this distance, we will call it as x1, we have a parabola. Now when you know that the strain is going to be limited to 0.002, can we calculate this x1 in terms of xu? We can calculate it easily, right? I am going to write it and then I am going to erase it later. So from similarity, you will see that x1 by 0.002 is going to be equal to xu by 0.0035. So x1 will become 4 by 7 xu, isn't it? So this distance is 4 by 7 xu, and correspondingly this distance is 3 by 7 xu. So here's some easy way to remember this. Okay. All right. Now, what is the force? Force is going to be C1 plus C2. So this is going to be your 0.45 FCK, because I forgot that in concrete we are going to apply correction factor 2 times. So this FCK divided by 1.5 is going to be your maximum stress, and then when you are doing the design we are going to apply again 1.1 by 5, that makes it as 0.45 FCK. Alright, so now let's calculate our C1, C2. So C1 is nothing but 0.45 FCK into 3 by 7 XU, which is the area of rectangle, into width. C2, if we consider only the rectangle that is circumscribing this particular parabola, so we will have 0.45 into FCK into 4 by 7 XU, then into B. Now since it is the rectangle, we know from our geometry class that if this is the parabola and we want the area of this can be approximated as 2 by 3 the area of this particular rectangle. So we have calculated the area of this rectangle. Now we multiply this by 2 by 3. So this is going to be your C1, C2. So if you want to approximate this, or we want to simplify this, 0.1928 FCKBXU and 2 by 3 into 0.45 into 4 by 7, 0.1714 FCKBXU. When you add this to, you get something around 0.364, which we write it as 0.36 FCKBXU. Alright. So I hope you understand how we get this C. Okay, and similarly, what you can do, you can calculate this distance also from the centroid, that 0.42 we get. So this will have somewhere around x 3 by 14. This particular C1 will have its centroid around 3 by 14, and then C2 will have somewhere here. So from the top you have to take the distance. I don't remember exactly the formula for the centroid of the parabola. I think it is something 5 by 8, but I don't want to take chances and make a mistake. So just you remember that when you add this C1, C2, you get a big C force, total C force, and that is going to be 0.42 away from the XC. Alright. Okay, so now that we know this, let's calculate our MU limiting. C into lever arm. 0.36 into FCK into B XU limiting into our lever arm, that is D minus 0.42 XU limiting. So we'll put the value 0.36 into 30 into B, that is 500. XU limiting we calculated 372 into D, that is 700 minus 0.42 into 372. So remember that whatever the result you are going to get, we have to multiply it by, divide it by 10 power 6 to convert it into kilonewton meter. So 0.36 into 30, 500 into 372 to 700 minus 0.42 into 372. We get a very big quantity, that is 1092.3 kilometer meter. So this is, this big amount of momentum it can resist when you talk about limiting momentum resistance. But what do we see again here? What else do we see? That this is not actually the amount of bending moment that is being provided or put on this particular beam. We are only putting 300. So mu limiting, let me write it here so that I can use this space. Mu limiting is very greater than mu that is put on this particular beam. That means we have to design a under reinforced beam. Now we cannot use XU limiting in LSM for under reinforced beam. So in case of WSM, we could design this same as balanced beam if it was under reinforced, and we can get away with it. But in case of LSM, you cannot do that. So we have to calculate our XU again. Okay, so we will calculate our XU. How do we calculate our XU? XU is calculated, C is equal to T. Whatever is your compressive force will be equated to your tensile force. So compressive force we have just now calculated 0.36 into FCK into B into XU. And tensile force is 0.87 into Fi, this is the stress in the steel, and AST. But wait a second, we don't know AST. So now you know that we have to calculate our XU and we have to go back to calculate our AST through a quadratic expression or through concrete expression. We can use any of them. Okay, so let's see what we get. We have to calculate our XU in terms of AST. So 0.36 into 30 into 500 into XU is going to be 0.87 into 250 into AST. So XU is coming out to be 0.06712 AST. Okay, this is the formula for our XU. And how can we calculate XU? We can equate this mu to again our 0.36 FCK XU into D minus 0.42 XU, and then we can get the value of our AST. Or what we can do, we can equate this to 0.87 into Fy into AST into D minus XU, and then we can get. In both the cases, we are going to form a quadratic expression. So it's we cannot avoid getting a quadratic expression. So let's use the steel itself. Let's use the steel expression itself. So we have 0.87 into 250 into AST into 700 minus 0.06712 AST, and this is equal to 300 into 10 power 6. So let us simplify some of the things. 0.87 into 250 is going to be 217.5. That into 700 is going to be 15250 AST minus 217.5 into 0.06712. 6712 14.5986. Oh, I forgot this thing. Here you have to multiply 0.42 XU, right? So 0.42. This will multiply with 0.42. So this will turn out to be 6.1314 AST square. This is equal to 300 into 10 power 6. Now when you solve this expression, so before solving it, let me write it in a general or a good form. 6.1314 AST square minus 152250 AST, and then plus 300 into 10 power 6 equal to 0. So AST basically will be 152250 minus 152250 square minus 4 into 300 into 10 power 6 into 6.1314 divided by 2 into 6.1314. Why am I only doing minus? Because you can see already the value is so high here for the B, and if I again add this value, this AST is going to be very, it's going to become very high, which is not feasible. So if we are going to take the lower value, and you will see that it makes sense. Square minus. So upon simplification, you see that this value is 26. So let me divide by the denominator also and give you the final answer. So the final answer is 2157.98 mm square. This is the area of steel that is required. Now you see, as I said, giving the minus sign also gives us this answer. So you can imagine if we were to add them and then get, it is going to be very high quantity, right? So that much still we cannot provide. We have to also use a little bit of logic when we are solving these quadratic expressions. Okay, so this is the area of steel, and if you remember, I told in the earlier when we solved this question that you can see that even by using a lower grade concrete, lower grade steel, and with almost the same area of steel, we are able to resist the same bending moment which we could resist by using a very high grade steel in case of WSM, right? And that's why I think one of the reasons why WSM method has been become obsolete, because it is not economical. So that's all for today's session. I hope, like me, you guys also had a revision of your WSM and LSM methods, and we'll meet again on next week. Have a nice week.